All right, so this is um, topic 8, and then when we get to the HL stuff, it'll be 18. So topic 8/18. We're covering 8.1 and 8.2 today. So let me scroll down. Okay, so 8.1 deals with what we call the theories of acids and bases. And it's kind of like the types of acids and bases. So there's more than one description for an acid and a base. The one we're going to be focusing on in the SL level is called Bronsted-Lowry acids and bases. And so the definition has to deal with protons or hydrogen ions, because hydrogen ions are the same thing as protons. Because if a hydrogen atom loses its valence electron, it really is just a proton in its nucleus. That's all it is. So when you hear the word proton donor or H plus or hydrogen ion donor, that's literally saying the same thing in this topic. Okay. The other type is that we're going to talk about is the Lewis acids and bases, but we don't get to that until the HL material. So for today, we're really just going to focus on the Bronsted-Lowry definition of acids and bases. And then we're also going to talk about a couple other terms, amphiprotic or amphoteric. We're going to talk about the difference between those. We're going to talk about how you can identify conjugate acid-base pairs and what that means. And then if you're given a chemical equation, a chemical reaction, you have to figure out which substance is acting as the Bronsted-Lowry acid or the Bronsted-Lowry base. And you have to be able to pair up where is the acid and the conjugate base, and where is the base and the conjugate acid. And you have to be able to identify those pairs in chemical reactions. It says here Lewis theory is not required. That's because it's in HL. Okay, so we'll get to it later. And then one thing to be aware of, guys, when we talk about acidic solutions or aqueous solutions that are acids, we talk about it in terms of hydrogen ions being in the water. So acids are characterized by having hydrogen ions in their solution. But sometimes you will see it written like this, which is the hydronium ion. And that's because typically what happens in acidic solutions is your water molecules, they will react or kind of take the proton from the hydrogen ion, and they will form this H3O plus ion. So if you see H plus and H3O plus, they use those interchangeably. They mean the same thing. They're both talking about the concentration of the hydrogen ions. Okay. All right. 8.2 is really properties of acids and bases. So we're going to talk about some of the types of some of the common chemical reactions. Like acids always react with metals. They react with oxides that have metals in their formula and hydroxides that have metals in their formula. They also react with hydrogen carbonates and then carbonate formulas. So there's several different types of reactions that acids can do and they react with. And we'll talk about sort of what products they will have, how to balance their equations, and that kind of things. All right, so the very beginning, it just had some common names and formulas. And if it's a weak or a strong acid or base, the names, you guys should be able to do most of these. The ones that you guys might not be able to do just from what we learned previous years, the ethanoic and the methanoic, because those are organic acids. Ethanoic acid is the same thing as acetic acids, like vinegar, okay? Methanoic acid is going to be a little different. So you might have to kind of look those up. The other ones, though, those are all acids that you should know how to name. And then the last few, these are bases. So you should know how to write their formulas from what we did in 10th grade. Ammonia is the only one that doesn't really follow the naming format for like ionic compounds and stuff. Ammonia is just NH3. Okay, NH3. There we go. I can't get the 3 to write. If you, as far as if it's weak or strong, I'm gonna let you guys, y'all can look that up and figure it out, and then we'll go over it next time and see if anybody has questions on it. Okay, so 8.1, Bronsted-Lowry. So the definition of a Bronsted-Lowry acid is it is a proton or a hydrogen ion donor. That means if something has extra hydrogen ions in its formula, it is most likely going to be the Bronsted-Lowry acid. If it doesn't have hydrogen in its formula, guess what? It can't be a Bronsted-Lowry acid because it doesn't have any protons to donate. On the flip side, a Bronsted-Lowry base, it's the opposite. A Bronsted-Lowry base, it's a proton acceptor. So typically your Bronsted-Lowry bases, they will either, sometimes they will have a negative charge on them. That usually indicates they can accept that hydrogen ion. Sometimes they won't have a negative charge, but they might have a lone pair on their molecule, because lone pairs means that they can accept a hydrogen ion and they'll form a coordinate covalent bond, okay? Because the lone pair will be the pair of bonding electrons, instead of each substance donating one electron, like a normal covalent bond, the bronzosylary base will form a coordinate covalent bond by donating both of its electrons, okay? So I said the proton is H+, but in solution, we identify it as the hydronium ion because it's always usually going to pair up with water molecules in the solution. So this reaction below, this is ethanoic acid, which ethanoic acid, we kind of learned that in 10th grade, it's acetic acid. In IB, we really refer to it as ethanoic because that's the organic name for it, because really it's an ethane molecule. It's got 2 carbons. And then it has the functional group for a carboxylic acid. And the stuff I'm talking about is what we're going to get to when we get to organic, how to name all of these different organic molecules. And so F means that it has 2 carbons in the chain, and then anoic acid means that it has a specific functional group, which is a specific grouping of elements that are attached to the molecule. So in this case, here's the 2 carbons, that's the F part. And then anytime there's a double bonded oxygen and an OH bonded on the end, that tells me that it's an acid. So it's an ethanoic acid because it's 2 carbons. If there were 1 carbon in the chain, that would be methanoic acid. If there were 3 carbons, it would be propanoic acid. And that's kind of how it changes. So this first thing is the ethanoic acid, okay? And so it's reacting with water to form the ethanoate ion and the hydronium ion. So what's happening is this acid has this hydrogen that it's going to donate this hydrogen ion. It's going to give it to the water. It can do that because water has these lone pairs. So water can allow it to form a coordinate covalent bond, and it can make the hydronium ion. That's the second thing over here. So we end up with the ethanoate ion. So now it's in brackets and it's got a negative charge because it didn't just lose the hydrogen, it lost the hydrogen ion. So it lost that positive charge, which means it goes from being neutral to being -1. The water is now the hydronium ion, which is H3O with a +1 charge. And that's because originally the water was neutral. Because it gained a H+, it has to have a positive charge now. It's no longer neutral, okay? And so in this example, ethanoic acid is the Bronsted-Lowry acid. And in this example, water is acting like the Bronsted-Lowry base because the water molecule accepted the hydrogen ion. It accepted the proton, okay? These reactions are doing the, showing the same thing, okay? So if you look, both of these reactions down below here are giving us the same information. The only difference is the first one is showing us the hydronium ion, so it's actually showing us the water. It's including the water as part of the equation. The other one is just showing us what happens when you dissolve that acid in the water, okay? And so it's leaving out the water molecule, and so we just end up with hydrogen instead of hydronium on the other side, but they're showing the same basic information, okay? So this one is just going to have you identify the Bronsted-Lowry acid and base in the forward reaction and in the reverse reaction. So if I'm going this direction forward, which of these reactants would be acting like the Bronsted-Lowry acid and which would be acting like the Bronsted-Lowry base? And then if I did the reverse reaction, so if I go this way, now which of these would be the Bronsted-Lowry acid and the Bronsted-Lowry base? And they have the hydrogen ion kind of labeled on there, so to kind of help you out with identifying that. So that leads us to this next part, which are called conjugate acid base pairs. So this is where your Bronsted-Lowry acid is going to have a conjugate base, and your Bronsted-Lowry base is going to have a conjugate acid. They're only different by 1 proton. So their formulas are different by a hydrogen and a charge of +1. And so in the reaction below, ammonia is my base. The way I can tell that it is the base is because if I come over here to the product side and, and I look at the molecule that has nitrogen and hydrogen, it has gained a hydrogen ion. It went from 3 to 4, and the charge went from neutral to +1. So that means that this NH3 accepted a proton, which means it has to be the base. And that means that the NH4 plus is the conjugate acid, because that's how they're always paired up. On the flip side, the water in this equation, the water is acting like the Bronsted-Lowry acid. Because if I look on the product side, the molecule that has hydrogen oxygens, it's got one less hydrogen and the charge went from neutral to -1. So that means it donated a proton or a hydrogen ion. So that means the water is acting like the Bronsted-Lowry acid, and this must be its conjugate base. Okay. So this is an example. So it says identify the conjugate acid base pairs in the following reaction. So the first thing I always like to do is before you even try to figure out which one's acid and which one's base, pair them up so that you can see how does it change from the reactant to the product side. Because if you pair them up, it's going to make it easier for you to tell, did it donate a hydrogen ion or did it accept and gain a hydrogen ion? So the first substance is this. So on the product side, which one is its conjugate? Which one do you guys think?
You said which one is which conjugate?
The one I underlined in red. What is its conjugate on the product side? Is it this or is it this?
It's the left one.
Yeah, it's the left one. So you want to look for which ones have similar formulas, right? Because their formulas are only going to be different by one hydrogen. So this is a conjugate pair. And that means by default, this is the other conjugate pair. So once you pair them up, now I want to go back and I want to say, okay, as this one went from here to over here, did it donate a hydrogen ion or did it gain a hydrogen ion in its formula?
Donate.
Yeah, it donates, right? Because here it has a hydrogen and it's neutral. Over here, it's got a negative charge and it only has 3 hydrogens. It lost that one on the end. So that means this is the acid and this is its conjugate base. Because the conjugate base is what's formed after the acid donates its hydrogen ion. So then kind of once you identify one pair, kind of by default, that means that this water molecule is acting like the base. And that means this hydronium ion is the conjugate acid. Okay. And you can also tell because it gained a hydrogen ion. It went from 2 hydrogens to 3, and the charge went from neutral to +1. And so water is a special substance because if you notice in this example, water was the base. But if I go back up to this one above, the water was the acid. And so water that's why usually we don't categorize water as being like an acid or any kind of specific type of compound, because it can actually act as both. Okay. And that kind of goes to this next section. Amphiprotic, the definition is a substance that can act as a Bronsted-Lowry acid or a Bronsted-Lowry base. So water is the most common example of an amphiprotic species, because in order to be considered amphiprotic, it has to be able to donate hydrogen ions, and it also has to be able to accept hydrogen ions. Okay. And water can do that. It has 2 hydrogen ions it can donate because it's H2O. So it has hydrogen in its formula that it could donate. And it goes from, if it's going to act like an acid and donate, it goes from H2O to OH minus. It becomes a hydroxide ion. But on the other hand, it can also accept. And the reason it can accept is because if we look at its Lewis structure, it has these 2 lone pairs. And so the lone pairs allow it to be able to accept and bond to a 3rd hydrogen. And in that case, it acts like the base, and it will then turn into that hydronium ion on the other side. Okay. And that's really what both of these examples are doing. In the first example, the water is acting like the base, because if you look, it's going from H2O to H3O plus. So that's like this. And so it's acting like the base. It accepted a proton. In the second example, it went from water to the hydroxide ion. And so that's like this one that I wrote down. And so in that case, it's acting like an acid. So look at what it turns into. So if you have water and you look on the other side and it's OH minus, then the water acted like an acid because it donated a hydrogen ion. If it turns into the hydronium ion on the other side, then that means it was acting like a base and it accepted a hydrogen ion. Okay. So sometimes we see this term amphoteric. Okay. It's kind of like a square and a rectangle. Okay. It's kind of like that definition. So you know how a square is a rectangle, like all squares are rectangles, right? But not all rectangles are squares. You know what I'm saying when I say that, guys? Because if you go to like your geometric definition for like square and rectangle, rectangle they have to have two sides that are the same. So this side is the same length, and then these sides are the same length, right? And they all have 90-degree angles. And squares, all four sides are equal. So by default, anytime you have a square also fits the definition of a rectangle. But a rectangle may not necessarily be a square. So it's kind of similar to that. Amphiprotic is kind of like the square. Amphiprotic is any substance that can both accept and donate a proton. So it specifically applies to the Bronsted-Lowry theory. Amphoteric is any species that can act like an acid at a base. And so there are other definitions of acids and bases, like I mentioned the Lewis definition that we'll get to in the HL. And so amphoteric is more broad. It's like any species that can act like an acid or a base. Amphiprotic specifically refers to this Bronsted-Lowry definition for acids and bases and accepting and donating protons. So that's why it says here all amphiprotic species are also amphoteric, kind of like all squares are by default rectangles. But all amphoteric are not amphiprotic. So it's a little bit tricky to understand, but hopefully, you guys can kind of put together that like amphoteric applies to all theories, even the Lewis theory. Amphiprotic specifically is talking about proton donors and acceptors, which is Bronsted-Lowry only. All right. All right, so 8.2 deals with the properties. So we're going to look at some different reactions. Acids and bases, when they react together, we call that a neutralization reaction. So you might hear it called an acid-base reaction or a neutralization reaction. That means the same thing. And they always produce the same thing, water, H2O, and they produce a salt, which is an ionic compound. So this is kind of the basic structure. Acid plus base makes salt plus water. And then here, these are a couple of different examples. So in this one, acid is hydrochloric acid. In this one, the base is sodium hydroxide. And so the H from the acid and the OH from the base come together to form the water molecule. And then that leaves Na and Cl together. And so I put them together for the ionic compound, NaCl. That's the salt. In the second example, this one is ethanoic acid and sodium hydroxide. And so again, the hydrogen and the hydroxide come together to form the water, and that leaves the sodium and the acetate or the ethanoate ion. And so it makes sodium acetate or sodium ethanoate. Okay. Acids can also react with metal elements that are reactive. So that means they have to be higher than hydrogen on the activity series because they have to be able to replace the hydrogen in the acid formula. And on this one, the general form is you're always going to get hydrogen gas and then an ionic compound from the metal and the negative ion. So in this one, magnesium is the metal. It's going to try to replace the hydrogen. And so it kicks it out and you end up with magnesium nitrate. And then here's my hydrogen gas. For carbonates and hydrogen carbonates, carbonates and hydrogen carbonates are also typically considered bases. They're not strong bases usually. And so they have a similar reaction to where they're always going to make water. Okay. But instead of forming just an ionic compound, it usually forms an ionic compound and also carbon dioxide gas. So it makes gas bubbles. So this is why if you ever eat like Tums, because Tums are calcium carbonate. So this first equation is what happens in your stomach if you eat Tums. So if you have an upset stomach and you go eat some Tums, what happens is the calcium carbonate that is in the Tums tablets, it gets to your stomach, it reacts with the hydrochloric acid, and it makes this stuff. So water, which is a liquid, it's neutral. It makes some calcium chloride, which is just a salt with some ions that doesn't really do anything to you, but it makes carbon dioxide gas. So sometimes if you take Tums or some of those over-the-counter medicines for your stomach, they will it'll cause you to burp. Sorry, I couldn't think what I was going to say, because it'll cause that the carbon dioxide gas is produced in your stomach and it has to come out somewhere. So usually you burp it up. Okay. The second equation is similar. The only difference is instead of a carbonate, it's a hydrogen carbonate. So hydrogen carbonate is also called bicarbonate. So this is hydrochloric acid and sodium hydrogen carbonate or sodium bicarbonate, which is baking soda. So you could also have this reaction with like vinegar and baking soda. It would instead of HCl, it would be the acetic acid or the ethanoic acid formula. But you get a similar thing. You get the salt and you get carbon dioxide and water. Okay. The only thing on here is that notice that we had to put a 2 in front of here to balance it, because the hydrogen here, there's no 2 because you have an extra hydrogen in your base, in your hydrogen carbonate. Okay. So it has you kind of practicing balancing some of the equations. And I think that is it, because the next section is 8.3. So do you guys have any specific questions about any of the information or examples from today?
No.
No, pretty straightforward.